We are in chapter 6, where we are discussing transformation of stresses and strains, failure theories, and thin-walled pressure vessels. This is the 49th session, and here we'll discuss three failure theories: Tresca's theory, von Mises theory, and maximum normal stress theory. This is the roadmap of the sessions covered in the first 4 chapters. We'll be discussing theories of failure now. Theories of failure were briefly discussed at the end of the second chapter, that is session 12, and at the end of the fourth chapter, that is session 36. We have covered shear and also transformation of stresses and strains. We now look at failure theories. In this session, we cover 3 of the failure theories. In the next session, we'll cover the 4th theory and then look at examples. We mentioned about theories of failure at the end of chapter 2 and the end of chapter 4. The normal stress theory and the shear stress theory has been used throughout starting from chapter 1. For bars subjected to axial loads, we have used normal stress theory. For circular bars subjected to torque, we have used shear stress theory. For beams subjected to transverse loads, we have used shear stress theory for shear and normal stress theory for bending. Now let us consider a structure subjected to different types of loads. Consider a point A for which this element is shown. In general, this element will be subjected to both normal stresses and shear stresses. If we rotate the element, then at a certain stage, it will be subjected to principal stresses. The principal stresses can be tensile principal stress and compressive principal stress. With rotation of the element at a certain stage will also be subjected to the maximum shear stresses. Now, such rotation of element can be carried out for all points in the structure. We can then find the absolute maximum tensile principal stress and the absolute maximum compressive principal stress. These stresses can be compared to the allowable tensile stress and the allowable compressive stress to check for failure. Also, we can find out the absolute maximum shear stress acting on the body. This stress can be compared to the maximum allowable shear stress to check for failure. For cases considered so far, all the absolute maximum principal stresses were found in sections perpendicular to the axis of the member. For members subjected to axial loads, any perpendicular section within a portion could be taken, and any element within the sections gave us the absolute maximum principal stress. With torque, also, any perpendicular section could be taken within a portion. Any element on the surface gave us the absolute maximum shear stress. With bending, at least in certain cases, only one perpendicular section was related to the absolute maximum principal stress. However, here also there was a group of elements that was subjected to the absolute maximum principal stress. The scenario with shear stresses in beams was similar. We have dealt with cases where both bending, and axial forces act. Here the normal stresses at an element had to be algebraically added up. But here also the absolute maximum principal stresses were found when sections perpendicular to the axis was taken. In all these cases, we did not need to rotate the element. Now consider the most general of cases. Here the structure is subjected to different types of loads. So sigma x and sigma y are due to different types of loads, which has to be algebraically added up. Similarly, tau xy is for different types of loads that cause shear stress. This element can be rotated and we can find the principal stress. As such, we can find the absolute maximum principal stress in tension and absolute maximum principal stress in compression. Similarly, we can find the absolute maximum shear stress. They can then be compared to the allowable values. For this general case, commonly rotation of the element will be needed. We have just studied transformation of stresses, and it will be put to use with theories of failure. In this session, we'll study maximum shear stress theory or Tresca's theory, von Mises theory or maximum distortion energy theory, and normal stress theory. We'll compare the theories with experimental results. In the next session, we'll study Mohr's theory. We'll also look at examples related to different types of theories in the next session. So in this slide, we have briefly discussed the way theories of failure are integrated to the whole analysis. We now start discussing the theories. Different failure theories have been developed by observing different kinds of materials. Thus, there are theories developed by observing failure of ductile materials and theories developed that applies well to brittle materials. We discuss here two theories that has been obtained by observing ductile materials. They are the maximum shear stress theory or Tresca's theory and maximum distortion energy theory or von Mises theory. Failure in ductile material often occurs by slip along shear planes. We earlier developed Mohr circles for such an element as shown. Let us consider that the stresses on the right face of the element are plotted here, and the stresses on the top face of the element are plotted here. Joining these 2 points gives a diameter of the Mohr circle. If we rotate the diameter, we get the whole Mohr circle. Earlier, we found out this formula for maximum and minimum shear stress. This formula is related to these 2 points. So we get sigma x, sigma y, and tau xy from these 2 points. We can use any 2 points on either sides of the diameter to find out tau max and minimum. So we can use sigma 1 and sigma 2. Then within this bracket, we get sigma 1 minus sigma 2. the corresponding shear stress is 0. So tau max minimum is given by this formula, or tau max minimum is equal to minus sigma 1 minus sigma 2 divided by 2. As per Tresca's theory, maximum shear stress decides when yielding will occur. Consider a body subjected to tensile stress only. As per Tresca's theory, yielding in given bodies will occur when the maximum shear stress equal to that of a body yielding under tension occurs. Consider sigma 2 is 0 and only tensile stress acts on a body. So we'll follow the normal stress line and the body will yield when sigma 1 is equal to sigma yield. We can develop a Mohr circle as shown. We can see from the Mohr circle that the maximum shear stress then will be sigma yield divided by 2. We can see the same thing from this equation with sigma 2 is equal to 0 and sigma 1 is equal to sigma yield. If we look at elements, then this element corresponds to this point, and this element corresponds to maximum shear stress of this point. As per Tresca's theory, this element gives us the criteria, not this element. Once we have found out the tau max that corresponds to failure, we can move this Mohr circle around. Tresca's criteria will follow as long as tau max is this value. Here we need to understand two differences that are particular to this chapter. The Mohr circle drawn here is not related to failure. It can be for any stressed element. If the element is rotated, we get this Mohr circle. This Mohr circle, however, is related to failure. Such Mohr circles related to failure will be commonly seen in this chapter. Consider a stressed element with stresses given by point A. As the element is rotated, will attain these stresses. So the point A does correspond to failure. Also, in previous discussions, we have considered sigma 1 as the maximum principal stress and sigma 2 as the minimum principal stress. Here, the principal directions are fixed beforehand. So, sigma 2 can be the maximum principal stress and sigma 1 the minimum principal stress as well. As earlier mentioned, the criteria of failure as per Tresca's theory is that tau max is equal to sigma yield divided by 2. As can be seen from any Mohr circle, the difference between the principal stresses is equal to twice into tau max. So one can interpret the criteria for failure as the difference between the two principal stresses being equal to sigma yield. So for the three-dimensional cases, we get sigma 1 minus sigma 2 is equal to plus or minus sigma y. Sigma 2 minus sigma 3 is equal to plus or minus sigma y. And sigma 3 minus sigma 1 is equal to plus or minus sigma y. However, as earlier, we are interested more in the cases with sigma 3 as 0. Considering sigma 3 is equal to 0, we get 6 sub-cases of Tresca failure criteria. We'll discuss them one by one. For all these 6 cases, the overriding criteria is obviously that tau max is equal to sigma yield divided by 2. So that is when failure will occur. Now in case A, sigma 1 is greater than 0 and sigma 2 is less than 0. Failure occurs when sigma 1 minus sigma 2 is equal to sigma y. In case B, sigma 2 is greater than 0 and sigma 1 is less than 0. Failure occurs when sigma 1 minus sigma 2 is equal to minus sigma y, or sigma 2 minus sigma 1 is equal to sigma y. In case C, both sigma 1 and sigma 2 are greater than 0. Failure occurs when sigma 1 is equal to sigma y. Again, in case D, both sigma 2 and sigma 1 are greater than 0. However, here sigma 2 is greater than sigma 1. Failure occurs when sigma 2 is equal to sigma y. In case E, both sigma 1 and sigma 2 are less than 0, and sigma 1 is less than sigma 2. Failure occurs when sigma 1 is equal to minus sigma y. Again, in case F, both sigma 2 and sigma 1 are less than 0. Sigma 2 is less than sigma 1. Failure occurs when sigma 2 is equal to minus sigma y. Instead of writing 6 equations, we can write 3 equations if we use absolute value. So case C and E can be given as absolute value of sigma 1 is equal to or less than sigma y. Case D and F can be given as absolute value of sigma 2 is equal to or less than sigma y. And case A and B can be given as absolute value of sigma 1 minus sigma 2 is equal to or less than sigma y. We discussed 2 elements for this case earlier. Let us discuss 2 elements for this case, as shown here. Notice that this element, which gives the failure criteria, remains the same. But this element is different with different stresses acting. This is the Tresca envelope. It consists of 6 straight lines, which are given by these 6 cases. These 2 points are sigma y, and these 2 points are minus sigma y. The criteria was obtained using this Mohr circle. Here sigma 1 is equal to sigma yield and sigma 2 is 0. So it gives this point. In the Tresca envelope, we plot only the principal stresses. Now let us consider case C first. It is given by sigma 1 is equal to sigma y. So it gives this line. Here we have sigma 1 is equal to sigma yield and sigma 2 as some positive value. So plotting will get this point approximately in the Tresca envelope. For this point, sigma 1 is equal to sigma yield and sigma 2 is some positive value. Now consider case D. The criteria here is sigma 2 is equal to sigma y. So we get this straight line. Here sigma 2 is equal to sigma y and sigma 1 is some positive value. So we get approximately this point. Sigma 2 is equal to sigma y and sigma 1 is some positive value. Consider case E. The equation is sigma 1 is equal to minus sigma y. So we get this straight line. Here sigma 1 is equal to sigma yield and sigma 2 is some negative value. So we get approximately this point where sigma 1 is minus sigma yield and sigma 2 is some negative value. With case F, we have sigma 2 is equal to minus sigma y. It corresponds to this straight line. Here we have sigma 2 is equal to minus sigma y and sigma 1 corresponding to some negative value. So with this point, we have sigma 2 as minus sigma y and sigma 1 as some negative value. Now for this case, we saw that the failure criteria is sigma 1 minus sigma 2 is equal to sigma y. The equation of a straight line is y minus mx is equal to c. So this is the equation of a straight line with slope. So this equation corresponds to this straight line. Here sigma 1 has a larger positive value and sigma 2 a smaller negative value. This is the approximate point with a larger sigma 1 value and small negative sigma 2 value. The criteria for case B is this equation, which corresponds to this straight line in the second quadrant. Here sigma 2 has a larger positive value and sigma 1 has a smaller negative value. At this point, sigma 2 has a larger positive value and sigma 1 has a smaller negative value. One would note that each point in the Tresca envelope corresponds to a whole Mohr circle. The blue circles here correspond to failure. Consider a point A in this figure. So the element at A has the stresses as given by the Mohr circle. If the element is rotated at a certain stage, it will have these two principal stresses, which correspond to failure in the Tresca envelope. So point A corresponds to failure, and all points in this Mohr circle corresponds to failure. Now consider this Mohr circle with sigma 1 and sigma 2 principal stresses. With any point in this Mohr circle, sigma 1 and sigma 2 will be the principal stresses. Sigma 1 and sigma 2, when plotted, was a point in the Tresca envelope, and as such is related to failure, which means any point in this Mohr circle is related to failure. Now in this figure, sigma 1 is equal to sigma yield, and we can vary sigma 2. Varying sigma 2 will give us this whole line. Similarly, we can obtain lines for the other 5 cases. One issue related to failure is the effect of hydrostatic stress. Figure A is shown here. Consider that apart from these stresses, the element is subjected to extra hydrostatic stress. If the hydrostatic stress is P, then the magnitude of all the principal stresses will increase by P as shown. The whole Mohr circle will move by the distance P. Since Tresca's criteria is related to the difference in the principal stresses, Tresca's criteria will not be affected. Here we look at a particular case, the case of pure shear, and plot the corresponding points on the Tresca envelope. Pure shear sigma 1 is equal to sigma 2 in magnitude. For Tresca's criteria, this is the equation for the fourth quadrant. So if sigma 1 is 0.5 sigma y, then sigma 2 is minus 0.5 sigma y, which is plotted as point B. For Tresca's criteria, this is the equation for the second quadrant. If sigma 2 is 0.5 sigma y, then sigma 1 is minus 0.5 sigma y, which is plotted as point A. When we consider pure shear, these two diagrams convert to figure 5. These two Mohr circles in figure A and these two Mohr circles in figure B becomes Mohr circle of equal radius. We now look at von Mises theory. It is also referred to as maximum distortion energy theory. There is another theory, the total energy theory. In order to understand maximum distortion energy theory, we need to understand total energy theory. So here we explain total energy theory first. Here we have an infinitesimal cube subjected to a stress sigma x1. Let the strain corresponding to sigma x1 be epsilon x1. The stress is increased gradually from 0 to sigma x1, and the strain increases to epsilon x1 from 0. As per Hooke's law, the stress-strain curve is linear. The modulus of elasticity E is the slope of this straight line. Now the total strain energy imparted by this stress is half force into distance. The force is sigma x1 dy dz. So this is the force. The distance is epsilon x1 into dx. So the total elastic strain energy U is half sigma x1 epsilon x1 dx dy dz, or half sigma x1 epsilon x1 dv. If dv is 1, then this shaded area gives the total strain energy. We'll now generalize. Consider an element subjected to all these stresses that normally act on an element. Then the total strain energy is given by this expression. There are 3 normal stresses and 6 shear stress that act on this element. The energy due to the 6 shear stresses are given by these last 3 terms. The energy due to tau xy and tau yx is given by this one term. Similarly with the other two. Consider that this element is rotated so that it is aligned with the principal directions. Then the elastic strain energy is given by this expression. Replacing strain by sigma and E, we get this expression. Consider an element to be subjected to one stress only, and that one stress is taken up to yield. Then the strain energy as per this term will be given by the left hand side of this expression. Substituting epsilon in terms of sigma and E, we get this expression for total strain energy at yield. As per total energies theory, when the total strain energy as given by this expression equals the total strain energy at yield, then the element fails. Equating the two expressions, we get this equation which gives the failure criteria according to total energy theory. This failure criteria is in 3 dimensions. If we have sigma 3 as 0, then we get this equation which is for the biaxial case. These are the stresses that will act on an element. Generally, the total energy of the element can be divided into 2 portions. One portion of the energy of the element is taken up by volume change of the element. The second portion of the energy is taken up by distortion. As per von Mises' theory, it is the distortion portion of the energy that is responsible for failure. Experimental results show that hydrostatic pressure has no effect on the failure of metals. We earlier saw that Tresca's failure criteria is aligned with this fact. A change in hydrostatic pressure does not affect Tresca's failure criteria. Now, hydrostatic pressure causes only volume change. So von Mises' theory is also aligned with the fact that hydrostatic pressure will not affect failure. We earlier discussed bulk modulus. It was mentioned that shearing stresses do not cause any change in volume. As earlier discussed, let us consider a unit cube subjected to normal stresses sigma x, sigma y, and sigma z. No shearing stresses act on the element. Then, due to the stresses, the lengths of the sides will change as shown. The total volume of this dotted cube is the multiplication of these 3 sides, or the length of these 3 sides. Ignoring small values, we get the volume of this dotted cube as 1 plus epsilon x plus epsilon y plus epsilon z. The initial volume of the unit cube was 1, so this is the expression for the change in volume. E is referred to as the dilation. Consider a body of volume V. Then the change in volume would be E into V. Since E gives the change in volume of a unit cube. Now here epsilon x is equal to sigma x minus nu sigma y plus sigma z in brackets divided by E. Substituting epsilon x, epsilon y and epsilon z in this formula, we get dilation by this expression. So dilation depends upon the sum of the three normal stresses. In the case of hydrostatic pressure, sigma x, sigma y and sigma z are all equal to P. So dilation is given by this formula. Consider an element subject to general stresses. Let us rotate this element so that it is aligned with the principal directions. Then it will be subjected to principal stresses, which we can designate as sigma 1, sigma 2 and sigma 3. Let us denote sigma 1 plus sigma 2 plus sigma 3 divided by 3 as P and hydrostatic stress. We then consider that sigma 1 consists of P and some other stress, similarly with sigma 2 and sigma 3. So we can write sigma 1 is equal to P plus sigma dash 1, sigma 2 is equal to P plus sigma dash 2, and sigma 3 is equal to P plus sigma dash 3. Now from the very definition of P, we get sigma 1 plus sigma 2 plus sigma 3 is equal to 3P. Now substituting these values, we get 3P plus sigma dash 1 plus sigma dash 2 plus sigma dash 3 is equal to 3P, which means sigma dash 1 plus sigma dash 2 plus sigma dash 3 is equal to 0. Now we earlier saw that dilation depends upon the sum of the stresses. So if the sum of the stresses is 0, then there's no dilation, and this means that there's no volume change. Hence these three stresses only cause distortion. Hence in sigma 1, sigma 2 and sigma 3, P causes volume change and these three stresses causes distortion. We earlier gave the total energy in terms of principal stresses, which was given by this equation. Now out of this energy, some of the energy is due to hydrostatic stress. If hydrostatic stress is acting only, then sigma 1 and sigma 2 and sigma 3 here is all P. So we get the energy as half 3P square minus 2 nu P square, since these values are P square each. Now substituting P by this expression, we get the energy due to volume change. Now the energy related to distortion is equal to total energy minus the energy related to volume change. That is this expression minus this expression, which we have written here. Now this front term can be written as 3 divided by 6e. We have then squared this term and separated minus 1 and plus 2 nu. Now consider the squared terms first. So we consider these three terms in each of the expressions. So we get 3 minus 1 plus 2 nu. That is 1 plus nu into 2. Now consider the product terms. Then we get minus 6 nu plus 4 nu and minus 2. So we get 1 plus nu into 2. These terms can be written in this form. So we can write the difference of the principal stresses in squares. Now consider an element subjected to tensile stress only. So sigma 2 and sigma 3 is 0. We want to find out the distortion energy when there's yielding. So we substitute sigma y for sigma 1 in this equation and we get this expression. According to distortion energy theory, failure will occur when the distortion energy is equal to the distortion energy at yield failure under tension. So we equate these two terms. So von Mises theory is half bracket sigma 1 minus sigma 2 square plus sigma bracket sigma 1 minus sigma 3 square plus bracket sigma 2 minus sigma 3 square is equal to sigma y square. The biaxial case with sigma 3 is equal to 0, von Mises criteria is given by this equation, which can be written in this form. The failure envelope for von Mises criteria is in the form of an ellipse with AB the major axis and CD the minor axis. For the positive portion of the sigma 1 and sigma 2 axes, the von Mises envelope, like the Tresca envelope, passes through the point sigma yield. For the negative portion of the sigma 1 axis and the sigma 2 axis, also the von Mises envelope, like the Tresca envelope, passes through the point minus sigma yield. Now consider a point P on the failure envelope. This point P corresponds to principal stresses, which we can take as sigma 1P and sigma 2P. As we earlier saw the Tresca criteria, a point P corresponds to a whole Mohr circle. So for this point P, we can first form this Mohr circle, from which with sigma 3 is equal to 0, we get the other two Mohr circles. So any point in this Mohr circle is related to failure. So the point P corresponds to stress combination of failure for a large number of points in the Mohr circle. One would notice that here the difference between sigma 1 and sigma 3 is greater than sigma yield. So this is different from the Tresca criteria. Here the Tresca criteria and the von Mises criteria has been superimposed. The Tresca envelope, apart from passing through these 4 points, also passes through A and B. So the envelope of the von Mises criteria circumscribes the envelope of the Tresca criteria. We look at the stresses at pure shear Tresca criteria, and we can do the same thing with von Mises criteria. In pure shear, the magnitude of the principal stresses are the same. So these are the two cases. We substitute this case in the von Mises criteria equation. Then writing in terms of sigma 1 in the numerator of these three terms, we get sigma 1 square. So on the whole, we get 3 sigma 1 square divided by sigma y square. So we get sigma 1 is equal to minus sigma 2 is equal to sigma y divided by square root of 3. With this substitution, we get these values of sigma 2 and sigma 1. This combination corresponds to point C, and this combination corresponds to point B. Tresca criteria, we earlier saw that failure was considered to occur at these two combinations. So von Mises criteria predicts failure at a higher load combination. Till now, we have discussed two theories of failure related to ductile material. We'll now discuss two theories of failure related to brittle material. These are maximum normal stress theory and Mohr's theory. Maximum normal stress theory will be discussed in this session and Mohr's theory in the next session. As mentioned, we have used normal stress theory earlier in different chapters. One issue would be confusing. Earlier, when dealing with normal stress theory, it was not mentioned that we are dealing with brittle material or ductile material. Similarly, with shear stress theory, normal stress theory was used in relation to metals, which are ductile normally. This confusion will be cleared up at the end of this session. With normal stress theory, if the maximum principal stress exceeds the ultimate strength of the material, then the material is considered to have failed. Normally, we use a factor of safety. The ultimate strength of the material is divided by the factor of safety to get an allowable value of normal stress that can be used. If the maximum principal stress is found to be less than this allowable value, then the material is considered to be safe. Unlike ductile material, the failure of brittle material occurs with little deformation. Failure in such cases occur by cleavage. Normal stress theory was given by Coulomb, and the failure envelope with respect to normal stress theory is given as shown here. This equation gives two sides. One of the sides is given by positive value of sigma 1 being less than sigma ultimate, and the other side is given by the negative value of sigma 1 being less than minus sigma ultimate. These two sides are given by positive sigma 2 less than sigma ultimate and minus sigma 2 less than minus sigma ultimate. Materials often have cracks, and under tension the cracks will increase in size, and under compression the cracks will close. So in brittle materials, the ultimate strength in compression can be larger than the ultimate strength in tension. This failure envelope was given by Rankine based on that understanding. Here we compare experimental results with the theories. This helps us understand the validity of the theories. These are the classical results of Taylor and Queenie. They carried out experiments on tubings in isotropic conditions. The tubings were subjected to tensile stress and torsion. Due to tensile stress, it was subjected to normal stress, and due to torsion, it was subjected to tau. Sigma 0 here is the yield stress. The material considered were copper, aluminum, and mild steel. These are the envelopes due to Tresca and von Mises. One can see that von Mises criteria correctly predicts the yield strength, and Tresca's criteria is slightly conservative. Here, maximum distortion energy theory, maximum shear stress theory, and maximum normal stress theory has been compared. Both axes are normalized. When it comes to von Mises and Tresca's theory, sigma 1 has been divided by the yield strength, and sigma 2 has been divided by the yield strength. When it comes to maximum normal stress theory, sigma 1 is divided by the ultimate strength and sigma 2 by the ultimate strength. As we can see, the von Mises theory correctly predicts the yield failure of the ductile materials, and Tresca's theory gives conservative results. Cast iron failure results are correctly predicted by the maximum normal stress theory. Also see here that in the second and the fourth quadrant, one should not use the maximum normal stress criteria to predict the strength of ductile material, since the maximum normal stress theory will overpredict the strength. When it comes to failure, there are two types of resistances: resistance to separation and resistance to sliding. Failure occurs depending on which of the type of resistances is weaker. Here we will discuss failure under tension compression and failure under torsion. Consider tension compression. Under tension, a cast iron bar fails with a flat surface. The failure is related to principal stress. Also under tension, a mild steel rod fails by cup and cone fracture. This failure is related to shear. Under compression, duralumin fails at 45 degrees to the horizontal. Similarly, concrete fails at 45 degrees to the horizontal. Now let us look at torsion. This is a cylinder of sandstone subjected to torsion. Consider an element here subjected to pure shear. If it is rotated by 45 degrees, then it will be subjected to maximum principal stress and minimum principal stress. Failure is perpendicular to the direction of maximum principal stress. This is the picture of a cylinder of sandstone failing at 45 degrees. Consider a cylinder of mild steel subjected to torsion. Then the fracture is along a flat surface and is due to shear. So we see the opposite cases. In tension, if a object is weak in the normal stress direction, then the fracture is flat. If it is weak in shear, then the fracture is 45 degrees angle. In torsion, if the weakness is along the principal stress direction, then the fracture is at 45 degrees angle. If the weakness is in shear, then the fracture is in the flat surface. So we have seen some cases of opposite type of failure in tension, compression, and torsion. In all the topics that we have studied till now, when it comes to tension and compression, we have dealt with normal stress theory. However, as we can see here, failure can be by normal stress or failure can be by shear stress. The reason we use normal stress theory only is due to convention. An element subjected to maximum shear can be turned around by 45 degrees with the principal stresses acting on the element. So one can convert shear stress failure to the normal stress criteria. In the case of torsion, till now we have dealt only with the shear stress criteria. Here we see that the failure is due to normal stress, but it can be converted to the shear stress criteria. Again, using the shear stress criteria is customary in torsion.